Hey everybody, today we're going to talk about neural networks using Python's Keras package. First, for a little motivation. Model building can be really hard, especially when you're trying to tell a computer how to build a model in a certain way. How do you tell a computer how to partition these houses from these trees, especially when a computer doesn't know what a house or tree is? As a user, you could try your best to split up the houses and the trees by telling the computer to partition the groups based on clumps. However, this wouldn't be 100% accurate, as you can see how we have one additional house on the left side in the tree group and one additional tree within the house group on the right. This kind of partitioning is known as classification. The goal is to group images or data into certain groups. One example of this is a digit recognition, as you can see above, and a second example, like we've seen before, house or tree. Neural networks can use human pattern recognition skills similar to the neurons in human brains. The goal is to have the computer emulate these human pattern recognition skills on large data sets. You may be asking yourself, well, why Keras? Well, Keras has super simple, friendly API which makes it very easy to learn and use. Keras produces very high quality error messages compared to many other programming languages and many other packages. Simplicity does not result in reduced flexibility because Keras is still integrated with the TensorFlow functionality, and additionally, it is easy to run on a multitude of different platforms. Every neural network contains two basic components, an input layer and an output layer. This particular figure is an example of a multi-layered perceptron. A multi-layered perceptron contains an input layer, an output layer, and however many input layers in between, typically only one or two. Within each layer, there is a specified number of neurons. The number of neurons depends on a few factors that I will address very soon. As you can see, each neuron is connected to all of the other neurons in the subsequent layer as shown by the arrows in the diagram. Now let's say we want to build a classification model to identify house or tree. Two of our variables are the color, so either yellow or green, and the shape, kind of that square house style or the tree shape. As you can see right here, there are weights and parameters are used along the lines to adjust and transform the input into the correct output. As more observations are fed through the model, these weights are adjusted with the goal of lowering the loss function, something we seek to minimize. Think of it kind of like an error. And as we continue to feed more observations and more epochs through the neural network, backpropagation is used to reevaluate and adjust each weight until they're just right. Every neural network has exactly one input layer. It usually has one input neuron for every predictable variable. So in the house or tree example, we have two pieces of information about it, the shape and the color. So we will have two neurons. In the case of tabular data, something more common, the number of input neurons matches the number of rows in the input array. It is challenging to understand sometimes what goes on in the hidden layer because it acts sort of like a black box. Within this black box, the user can suggest an activation function to help figure out the nonlinear data. For most practical applications, no more than one hidden layer is necessary. In occasional situations, two hidden layers are used, but it doesn't generally improve performance. Two hidden layers are generally used in unique situations with complex algorithms, but you should always start with one hidden layer to start out. Having too many hidden layer neurons can result in overfitting and a slow runtime, while having too few hidden layer neurons can result in underfitting. Before we get too far along, I'm going to show you a few examples of some of the most common activation functions. One example, as shown in the top left corner, is the binary function, and it's good for classification where you have a binary response. Say, for example, whether you want to take a picture and see, is this a house or not a house? The sigmoid, shown in the top right corner, is good if your response is a probability since its support is continuous between 0 and 1. The hyperbolic tangent is useful for converting a linear predictor into a nonlinear response, shown in the bottom left corner. The ReLU, or rectified linear unit, shown in the bottom right corner, is good for a positive response since its support is 0 to infinity. Sometimes you have to play around with the activation functions since some are better at learning with certain kinds of data than others. It's okay to try several out and choose the one with the best results, but you should always try to consider what is the support of your data. For example, if you're looking at housing prices in the area, you can use the ReLU because all the housing prices are positive real numbers. Similar to the input layer, Every neural network has exactly one output layer. The output layer typically has only one neuron. However, sometimes it can have more than one neuron, and this is used when the softmax activation function is used. This is used in cases to normalize the output of a network to a probability distribution over predicted output classes, or if you're using categorical data. Now we're going to try implementing a neural network using Python's Keras package. Be sure to watch the next video to continue and see how this is done.